سنتكلم يوما عن الطقس الفضائي وما علاقة الطقس الفضائي بكوكب الأرض، وكيف يتم ترقب ومتابعة هذا النشاط، وهل يشكل النشاط الشمسي خطرا على الأرض؟ في هذه الجلسة سنتعرف على الطقس الفضائي ونجاوب على كل هذه التساؤلات مع جلسة مقدمة إلى الطقس الفضائي مع الدكتور مبشر الشيخ من جامعة الشارقة. هذه الجلسة مقدمة من جامعة الشارقة وأكاديمية الشارقة للعلوم وتكنولوجيا الفضاء والفلك.
Okay, Bismillahirrahmanirrahim. I'm Dr. Mubashir from Sharjah Academy for Astronomy and Space Sciences. First of all, my apologies for not speaking in Arabic, but unfortunately I'm still learning and I'm not able to present it in Arabic. So I hope that you understand and enjoy my presentation in English. Today I'm going to talk about the space weather. Since I'm talking to general public, I would like to be as general as possible. Just try to explain how things work in this solar terrestrial interaction, which we call, in which the sun is the main source of energy for us, and we are at the terrestrial side trying to take advantage of the sun's energy that it emits. So basically, what is happening? About 150 million kilometers away, our sun is a burning sphere of gas and charged particles. It can cause devastation on our modern world. For us, sun may appear very quiet and unchanging from day to day, but basically its behavior changing, its energy output changes according to a cycle which lasts for 11 years generally. And at the peak of this 11 years solar cycle, there are a lot of solar storms that disturb space weather events. They basically risk to the satellites which are surrounding the Earth and on the outer edge of the radiation belt, and put them into an environment where they are not originally designed for, basically. But this is what we have to take. We cannot change. So if you talk about close to the sun, what we have here is that a sun is full of, sun's atmosphere is consists of hydrogen, which itself is made of subatomic particles. These particles are coming continuously from the surface of the sun, following the open lines of magnetic field of the sun. Sun magnetic field and these charged particles join together and combined, they give us a wind. That's just like a wind on Earth. We have a wind from the sun full of these particles coming to us, and we call it solar wind. At the peak of 11 years, high solar activity may result in two types of event. It can be a solar flare, a very short burst of energy, and it can be a coronal mass ejection. Coronal mass ejection is an explosive ejection of a large amount of solar matter, and it can cause the average solar wind speed to take the dramatic jump. I mean, from normal one to up to many times higher. Somewhat like a shock wave heading towards Earth. Solar flares occur with magnetic energy that has built up in the solar atmosphere, releases very quickly. So it's a short burst of energy, these solar flares are. These bursts of energy are some of the very high energy solar system events, emit radiations across almost the full electromagnetic spectrum, from very low frequency radio waves to very high energetic X-rays and gamma rays. These short duration solar events release the amount of energy comparable to the millions of 100 megaton hydrogen bombs exploding at the same time. So you can imagine how much energy can be exploded. This is happening every second on the surface of the sun, and we are receiving a very fraction of it. Otherwise, the Earth may be burned up completely. The solar wind is constantly boiling off the surface of the sun and traveling towards us and other planets in the planetary system of the sun. Sun has a protective shield. We luckily have a magnetosphere. These purple lines are basically showing what we call a magnetosphere of the Earth. The magnetosphere is a region of space surrounding Earth where magnetic field of Earth is dominant, where we can protect ourselves from this harmful, high pressurized solar wind. the boundary between these two, where this yellow material from the sun and these magnetic liner forces of our Earth meet, it is called magnetopoles, where actually we are creating a pause for the high energy, high speed solar wind. This boundary is in continuous motion, as Earth is struck by the dynamic solar wind. Due to the continuous pressure from the striking solar wind, the magnetosphere has a bulging, a compressed effect. So you can see from the sun side, we can see the solar wind is being compressed, and from the other side, which we call night side, we have the rather expanded magnetic field. And this night side, where the magnetic field is expanded, or lines of magnetic forces are rather open, it is called magnetotail. Due to this reshaping of the magnetic field because of the sun's electromagnetic radiation, charged particles eject by the sun are guided into the ionosphere. So this is basically these solar wind particles are traveling across or along the lines of these magnetic field and entering into the pole side, where these magnetic lines of forces are merging at South Pole and North Pole. And then it can basically create a sphere within a sphere, which we call the ionosphere of the Earth. So what happens in the ionosphere, or what happened at the meeting point? Basically, although magnetopause guards us to some extent from the harmful solar wind on the day side, where we are facing the sun, it is far from impenetrable. I mean, it can be easily penetrated by the solar wind. So solar energy, mass, and momentum can be transferred from solar wind to the inside of the Earth's magnetosphere. The interaction between the solar wind and the Earth's magnetic field and different processes in the lower and upper atmosphere drive convection currents within the plasma in the magnetosphere, and then eventually in the ionosphere, which is the sphere inside this sphere. This in turn creates the plasma, the ring current. The ring current can be seen on the right side of the picture. These are the currents that are flowing across the Earth, perpendicular to the magnetic lines of forces in a ring shape. And this makes the condition inside the magnetosphere highly dynamic and cause this so-called space weather. So all these things, these currents flowing in and outside the into the ionosphere, and this radiation belts going across the Earth, getting intense when the solar wind intense, getting weaker when the solar wind is weaker, is all combined together. It's called the space weather of our solar system. The compression of the magnetosphere, together with the particle scattering by the wave, dumps large amount of charged particle into upper atmosphere, which is basically the ionosphere, but in particular close to the poles. Why close to the poles? Because this is where the magnetic lines of forces, these yellow lines shown in the left side of the picture, they are actually terminating. So these are bringing in the energy which they receive from solar wind and depositing it here in the upper atmosphere of the Earth. So let's go back and talk about how this solar wind is created and why it becomes intense, and what are the visible markers of these solar winds that can be created through the solar flares and CMEs. CMEs are coronal mass ejection, rather intense solar solar storms. The solar flares and solar CMEs have been studied for centuries. By counting the number of sunspots, so what we count these dark spots on the surface of the sun. They appear dark in the background of a yellow background of the sun. Basically in different wavelengths, if we study, we can see a full in the same sunspots in different activity level in different wavelengths. And they become more visible following a burst of radiation flare from the sun. These bursts of energy follow the blockage of solar energy, which occurred during the development of a solar flare. When the blockage of energy is released into the space, these radiation flares come out of the surface of the sun which are packed with the charged particles, leaving behind the dark spots. So basically, these dark spots are visual markers of some intense activity that has just happened at the surface of the sun. If these spots are towards us, or the burst of energy is towards the Earth or other planets, these planets then they experience the intense solar space weather. Otherwise, if these spots are not towards us, we don't receive the energy that are just being emitted through these sunspots, and we can save ourselves with our magnetosphere easily. So what happened when because of this intense space weather? Space weather is there all the time, but when it gets intense, it can harm everything that we are connected to. So violent space weather can cause geomagnetic storms on Earth, which can disturb communication and navigation satellites, interfere with electrical grids, and even it can affect high-flying airplanes. Disturbed space weather increase the risk of those satellites, basically, that are orbiting on the outer edge, the outer edge of our upper atmosphere. So if I can show you, these are the satellites which are basically almost at the edge of the upper atmosphere, and they are more vulnerable to this space weather because they receive the first impacts. They are close to the radiation belt, that's fine. Space scientists and engineers have observed several examples of loss. So we have lost a lot in terms of intense radiation hitting the satellites, and they go offline, or they go off operational. So some of them can be in 1970s, Skylab space station re-entered the Earth atmosphere. So because of the intense solar wind, it re-entered the Earth atmosphere and finally, obviously, burned up into the upper atmosphere. In 1997, a satellite called Telestar was lost completely, and later it was discovered that it was because of the intense solar event. 1995, Intelsat, and in 1996, GEO's 8 satellite. These are the few examples that we have lost. But anyway, generally, we are all at the mercy of intense space weather, if specifically people who are living close to the North and South Pole. But we have some good effects. I mean, these space weather effects, extreme space weather effects, if they can be seen in terms of aurora, they are very fascinating. So basically, it's all about solar wind entering into interacting with the magnetic lines, so magnetic lines of forces, entering through these lines of forces into the polar region, and that's where they actually interact with the oxygen molecules, and then with different compounds, they release different type of bright aurora light. So it may be purple, it may be green, it may be any other color which that interaction can produce at that time. So this is what we see in the ionosphere on the right side of my screen, and this is what actually is happening between the sun and the earth interaction, and how we are receiving that energy that creates this beautiful aurora near the high latitude or close to the polar region. But we are not doing nothing. We are actually sending a lot of satellites to know about these extreme solar space weather events beforehand, at least before few hours they reach the Earth. So in fact, there's a significant increase in research as studies regarding solar terrestrial interaction through the satellite data. And these studies combine analysis, interpretation of solar interplanetary and Earth space observations. Additionally, we have been busy in developing more satellites, more technologies to monitor and to measure the effects of solar wind. Models based on interplanetary information can forecast space weather, and about an hour or two ago, before the actually this plasma reaches the Earth and disturb us. We have some spacecrafts which have been there for some time now, and which some of them are very new. So like ACE and so have been there for a long time, and stereo voyages are the ones which are actually going there. I mean, they are there, and it's now like their responsibility to tell us what the space SOHO and ACE spacecraft have been doing, and helping us to predict or forecast the space weather. Just like we have so many satellites to forecast our local weather, we have these satellites to forecast our space weather through the measurements. And now this is about space weather. What we are doing at the Sharjah Academy for Astronomy, Space Science and Technology, we have actually two instruments with which we are monitoring the ionosphere, which is actually the last part of the solar terrestrial interaction. One of them is the ionosphere radar system. It is installed on the premises of the Sharjah Academy. This is the building of the Sharjah Academy for Astronomy, Space Science and Technology, and this is the 20-meter mast transmitter of the ionosphere radar system. What we receive through this, we actually receive the images of the ionosphere separating by 15 minutes. So every 15 minutes we operate our system, and we receive the image of the ionosphere. Through this image, we actually try to calculate how many layers are present, what layers have what intensity, and then we can insert this information into models to forecast what is the outer condition of the upper atmosphere. We also have the multi-constellation, multi-frequency GNSS receiving station with scintillation monitoring capability. And this tells us about how to disturb the ionosphere, specifically for the radio communication. So radio communication through satellites and through navigation satellites, which give us positioning for our traveling. It's very important to know whether we are receiving a clean data or not, in order to monitor, in order to predict whether we have a disturbance in upper atmosphere or not. We are continuously monitoring all frequencies on all four major GNSS constellations, which are one from US, which is GPS, one from Russia, which is GLONASS, one from Europe, which is Galileo, and one from China, which is Beidou. All four major constellations are being monitored and measured through their signals, L-band signals, at our academy, and we analyze the data and publish it whenever we have some good results to publish. So this is what I have to say. Basically, that's all by me, about introduction about the space weather, and then an introduction about the laboratory and what we are doing here at the Sharjah Academy for Astronomy and Space Sciences. So thank you very much for listening to me. Thanks a lot.